Okay, so we've got objects 1, 2, and 4. They all travel 2.45 meters. We just have to do 3 and 5. 3 is, I believe, the ball. Okay. We can do a similar approach. We can figure out how fast the ball is going when it gets to the bottom by determining, well, we could use forces and energy, or we could use forces and kinematics. I'm going to choose to use energy though. We know that, once again, ET equals ET, bottom of the ramp and top of the ramp. We know that initially it has gravitational potential energy, and we know at the bottom it has both the translational kinetic energy, and because the ball is rolling, it also has rotational kinetic energy. Notice that I think in choice number 2 there was also a ball, but it wasn't rolling, it was sliding. Okay? There was no friction. The difference here is now the kinetic energy is both translational and rotational. mgh equals 1/2 mv squared plus 1/2. Remember, for rotational kinetic energy, we're using 1/2 I omega squared, the angular velocity. Now here's what we're going to do with this. Let's start plugging in things that we know. We know that this h, the height that it drops on the ramp, is really L sine theta. mg L sine theta equals 1/2 mv squared. V is ultimately what we're looking for. I can't cancel out the m's yet, but I do know that the rotational inertia is 2/5 m, r being the radius of the ball, squared. And remember our little trick, if we want to relate the linear speed to the angular speed is equal to v over r. So instead of omega squared, I'm going to do v squared over r squared. Look what I have now. I have an m in every single term. Those will cancel. I have an r squared here and an r squared here. Those will cancel. I even have a 2 up top and a 2 down low. Those will cancel. What I'm left with is g L sine theta equals 1/2 v squared plus 1/5 v squared. Now, 1/2 v squared plus 1/5 v squared, we can do the math in your head. This is 5/10, this is 2/10. You add these together, we get 7/10 v squared. We bring this to the other side. Turns out that v, so we bring the 7/10 to the other side, it's got to be 10 over 7. We take the square root. This ends up being the square root of 10/7 g L sine theta. We compare that over here. It was 2 gl sine theta. This is very clearly less. 2 gl sine theta would be 14 over 7. This is only 10 over 7. The speed is less, just like we predicted. We already know the time for all 5 objects is square root of 2h over g. So now we just plug into the distance formula. Same things will cancel as last time. 0, 0. It's 10 over 7 gl sine theta times square root of 2h over g, excuse me. Let's see, the g's will cancel. We end up with the square root of 20/7 hl sine theta, which when we plug numbers in, sine 30. You can check this on a calculator. You should get that the distance it travels is 2.07 meters. Hopefully these are right, so you should check these for me. Okay? It doesn't go as far, just like we predicted. Finally, for 5, which is the hollow cylinder. I'm going to have to write small. I didn't leave myself a lot of room on this one. Okay? We still, again, we start off ET equals ET. For top and bottom. UG equals KT plus KR. we know this is mgh, 1/2 mv squared plus 1/2 I omega squared, mgl sine theta, 1/2 mv squared plus 1/2. Now, for a hollow cylinder, rotational inertia is just mr squared. Mr squared, omega squared would still be v squared over r squared. Again, cancel the m's and cancel these. I end up with gl sine theta equals 1/2 v squared plus, ooh, look at that, 1/2 v squared. 1/2 v squared plus 1/2 v squared is simply equal to v squared. Therefore, v, in this case, is the square root of gl sine theta. Again, which is less than this, which is less than this. So, we go to our distance equation. That's 0. That's 0. GL sine theta times square root of 2h over g. Cancel the g's. X is equal to 2HL sine theta, 2 times a meter times 3 meters times the sine of 30. X is 1.73 meters. As you can see, the hollow cylinder will not go as far. I invite you to please check my work on this, okay? Go through the math yourself. If you have questions, please ask, okay? I think these are cool problems because, again, we're stepping into something that's a little bit more complicated than you've done so far, but it's also a little bit closer to reality. Last thing. Last thing that you're going to look at for me. Another student says that another way of examining the problem is to realize that friction is acting on the objects that are rolling, slowing them down. This is true to an extent. Comment on the student's statement, making sure to include your response whether or not the student is correct. They are. What type of friction acts on the object, what the free body diagram for the object looks like, and what the acceleration of the object is compared to the acceleration of an object that slides instead of rolling. So they're saying the ones that don't travel as far, they have friction acting on them. The ones that slide, they do not have friction acting on them. It says that in the problem. No friction for 1, 2, and 4. 3 and 5 do have friction on them. It makes sense that they would travel less slowly. Less slowly. Slowly. More slow. Forget it. The student is correct. Now, if they are rolling, okay, rolling smoothly, that means that the point of contact of the object is not moving relative to the surface. There is no slipping. That means it's not kinetic friction, it's actually static friction, which is very interesting. Since static friction acts on the objects against their tendency. You know, the objects, if friction wasn't there, they would try, I say it like they have a will. They slide down the ramp. So, friction, the force, is directed up the ramp. And the objects experience a torque due to this friction about their center of mass, their centers of mass, I should say, and begin to roll. Now, I'm going to do some math to show you how the accelerations compare in each case. Let's see, we knew that we had this, we have an object on a ramp, pretend it's a circle. Let's see here, we know, oh god, that's really bad. I gotta change that. That's better. Okay, we know there's a force of gravity acting on them. We know we can split that into components. Here's Fg cosine theta. Here's Fg sine theta. We've got the normal force. We've got the force of friction. Okay. So our net force equation would look something like this. Where am I? Actually, do we even know the net force? I don't have one written down here. Yeah, okay, no, we'll do one anyways. F net x equals Fg sine theta minus the force of friction equals max, linear acceleration down the ramp. We know F net to y equals Fn minus Fg cosine theta. It's not accelerating though, so the normal force is just mg cosine. And we can also do the net torque. The only force, just like in the previous example, causing a torque is the force of friction. Equals I omega. Okay. Let's see here. So this would be R FF times the force of friction itself times sine theta for this force. That's going to end up being 1 equals, I'm going to use B for the coefficient, B, some coefficient times mr squared times, what is it? I'm blanking on stuff all of a sudden. A over R. That being the substitution for alpha. This, the distance that the force acts from the axis of rotation is the radius of the object. R times FF equals B M, radius of the object, times acceleration over radius. The r's will all cancel out. I am left with the force of friction is equal to that coefficient times the mass times the linear acceleration, ax. So, I didn't do this last time, but I have a trick here. I can plug this in for the force of friction. Again, I don't know whether this is the maximum force of friction. Doing mu Fn is not really going to work here. Let's see here. We have now mg sine theta minus b max equals max. I add this over to the other side. Oh, I can cancel out the m's, never mind. G sine theta equals ax plus b times ax. I pull the ax out. I get that the acceleration is g sine theta over 1 plus b. Now the reason that is important is because for an object that simply slides down the ramp, I have pretty much the same free body diagram. I have Fn, Fg, Fg sine theta, Fg cosine theta. For something that's sliding, for the ones that are sliding, we'll say that there wasn't friction. Okay, there was not friction, so I simply have this. I have the net force in the x direction is Fg sine theta, which equals max. This is mg sine theta equals max. Cancel the m's. We get the acceleration for the objects that slide is simply g sine theta. Which acceleration is going to be bigger? This or this? It's this one. Okay? We're dividing g sine theta by some factor bigger than 1. It's going to be smaller. Now, the one thing I will say with this is this seems like it reasons out pretty well. This is another thing. I am not 100% sure of this reasoning. It seems like it makes sense. I also could see arguments for like, oh, you didn't take this into account. So again, if you want to look this up and to kind of look and do some research on this, by all means be my guest, then we can have a discussion about it. However, this is more or less right. You could reason it out this way. That being said, that's all I have for rolling. When you come back, we'll be talking about angular momentum and gravitation. These are the two video lessons that we've done. They've been fairly small topics. There's only a couple of homeworks for each. They are very involved though, so you do need to try them. At least a couple of questions from each would be really, really important for you to do. As I said in an email, don't try and do everything. I wouldn't, say I'm just going to do the torque ones. I'm not going to do any of the others. Get a sampling of each. All of them are going to be due eventually. Okay, even if you have to turn them in after the AP test, but you do need to have some exposure to these types of problems. Okay. Hope you have the last good few days of break, and I will see you on Tuesday. Bye.